Welcome to lecture 52 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. Myself Mukul Das from Electronics Engineering Department, IIT ISM Dhanbad. With me, Dr. Syed Sadiq Anwar Askari from Manipal University and Mr. Pranav Kumar from IIT ISM Dhanbad, assisting in the course as TA. In this lecture, we will cover effect of interface defect on the performance of thin film solar cell through demonstration of simulation using SCAPS 1D simulator. In the last lecture, you have observed the effect of emitter doping on the performance of thin film solar cell, and also we discussed in last class that absorber doping generally in the moderate or low, that is in the range of 10 to the power 14, and that's why we have not shown the effect of this absorber doping. It is generally kept in the range of 10 to the power 14 to 10 to the power 16 depending on the materials. Also, effect of temperature on the performance parameters has been shown through demonstration of simulation using SCAPS 1D. In this lecture, simulation will be done to observe the effect of interface defect on the performance of thin film solar cell. Interface defect is very important concerning thin film solar cell in particular. Let us see first what is interface defect and how these defects affect the performance. Before simulation, let us discuss briefly how it should affect or what effect of the performance parameters, say open circuit voltage, short circuit current, efficiency, etc., how they change with the defects. And after that, you will be observing the simulation process. Again, we consider the same structure, that is cadmium telluride based thin film solar cell. Already we discussed in last class and also earlier classes. And the material parameters also we set during simulation, also varied some parameters and shown how to vary these parameters to observe the effect. Here, if you observe, there are some parameters which are related to the interface defects. Though these parameters are not here, so thermal velocity, hole thermal velocity, electron thermal velocity, mobility, these are a bit related, but actually the defect density at the interface, that is not mentioned here. But in this lecture, after this theoretical discussion briefly, you will be observing that what is the value of interface defects or what are the defect densities for thin film or amorphous thin film solar layers are used or are obtained. So first let us discuss the interface defects. What is interface defects? It is also called the interface states. State means always it indicates some energy levels. And these energy levels located at either emitter or absorber interface in case of heterojunction or homojunction boundary. Say for example, cadmium telluride based thin film solar cell, these energy levels or energy states located at the interface between cadmium telluride and cadmium sulfide, or interface between zinc oxide and CIGS material, or sometimes absorber or buffer interface. Sometimes we use a buffer layer between emitter and absorber. In that case also, we may have some interface between absorber and buffer. Sometimes between absorber and back contact, some interfaces are there, and that interface also may have some energy states. So interface states means the energy states located at the interface between two different materials. And these basically arise from lattice mismatch or the dislocations, because suppose you have a cadmium telluride and cadmium sulfide junction. So in the cadmium telluride based thin film solar cell, this is say cadmium telluride and this is cadmium sulfide. These two different materials have a different lattice constants, but what at the interface? At the interface there will be two different types of lattice constants. In the bottom side there is a lattice constants of cadmium sulfide, and the top side there will be lattice constants in the cadmium telluride. So due to difference in lattice constants, there will be a force between atoms of two layers, and that energy, that force ultimately creates some extra energy states at the interface. So these interface states basically may arise from the lattice mismatch between two different materials. Also, it may arise from incomplete bonds or called dangling bonds. If you remember one picture in a silicon structure, very early classes, we have seen that, we have shown you that one silicon atom is surrounded by four silicon atom in a bonded structure. There is a covalent bond in this way. But if you observe the silicon atom at the surface of silicon bulk layer, suppose. So what about the silicon atom at the surface? This silicon atom is not getting any other silicon, suppose here, to make this bond, because these are the surface, but they may bonded with other silicon atoms in between, but in the left side and in the top there are no silicon atoms. So there is an incomplete bonding is there. So this may create a dangling bonds, incomplete bonds, and due to these incomplete bonds, the states, energy states of these surface atoms will be different from the energy states of the atoms well inside the material. So obviously some energy states will be appearing at the different level. So these energy states will not be as per with the band diagram, that is not within the conduction band or not within the valence band. So this may create also some defects or energy states or the interface states or surface states also you can tell. Chemical impurities or diffusion across layers. Suppose whenever you are fabricating some layers, cadmium sulfide layer, suppose. So this cadmium sulfide layer is deposited from the chemical process through some precursor solutions, some chemicals. So you cannot give a guarantee that only cadmium sulfide will be there. no other chemical impurities will be present. So due to presence of other chemical impurities, so that material have a different band structure. So obviously that material's band structure, band states of that atom, impurity atom will be different, and that may create also the states at the interface. Or whenever you are diffuse some material, suppose you are making a diffusion to make a emitter layer, you are supposed developing a crystalline silicon solar cell. So you start with a absorber bulk crystalline single crystal solar silicon layer, that is called wafer. After cleaning the surface everything, you are making an emitter layer through diffusion process. That is, you have to make a N-type silicon layer on a P-type crystalline silicon absorber. During this diffusion process also you are putting some impurities, like for N plus you are putting some phosphorus atoms. So in that case these phosphorus atoms may behave as a impurity. So this may create also energy states which is not within the conduction band or the valence band of the original atomic structure or host atoms. So that's why this may create also some states at the interface. And they mainly introduce the mid-gap states that can trap the carriers and mediate the recombination process, that is Shockley-Ridley recombination mechanism, you know. So these are the different mechanism of arising the interface states. Now, how these interface states affect the device performance? First of all, recombination. Because Shockley-Ridley recombination we have discussed, you have seen that if there are more and more interface states, there is a chance of more and more recombination. And carrier loss due to recombination will be more in that case also. So interface defect states capture electrons and holes, and this enables the Shockley-Ridley recombination right at the junction. Because why junction? Because at the junction there is interface between two different materials. So obviously the recombination occurs mainly near the junction, and this ultimately lowers the minority carrier lifetime and hence the diffusion length. And direct result, if you see, that is reduced short circuit current density, because out of the all photogenerated carriers, some are recombined, so they cannot be collected. So fewer carriers are collected. So obviously the JSC is expected to be reduced. Open circuit voltage, whether is there any effect on open circuit voltage? Yes, since the recombination lowers the quasi-Fermi level splitting, that is separation between quasi-Fermi levels, and which mainly determines the open circuit voltage, that will be also reduced. Because recombination takes place means the splitting between quasi-Fermi levels will be low. So due to the presence of this interface states, the recombination, both VOC and JSC are expected to be reduced. Band bending and barrier formation, that is another important thing we should have a knowledge. There is any charged interface states. Charge means sometimes at the interface some charged atoms are there. There is some ion, some may present. So negatively charged ions or positively charged ions, etc. So these charged interface states, they pin the Fermi level at the interface. And Fermi level pinning, it is called Fermi level pinning, and this basically modifies the band bending at the heterojunction, and that can create a cliff type conduction band offset. And offset means barrier in the from the one side conduction band to other side conduction band. Carrier cannot flow smoothly, and this cliff type conduction band offset, that is very bad, and that promotes the interface recombination. Due to this barrier, carrier will not be propagated smoothly, and due to presence of barrier, either carrier may cross the barrier through thermionic emission process or through tunneling process if the barrier width is very low. We have discussed this phenomenon also. earlier. So if there is a suppose thermonic emission process, so this is again a slow process, and during this slow time carriers may be recombined. So this barrier may boost the recombination process. So in this way also interface defects affect the performance. So on an unfavorable barrier for minority carriers, unfavorable means that is a offset, cliff type offset, which is not favorable for carrier flow, which is obstructing the carrier flow, and this blocking their transport, and both effects reduce carrier collection, thus the fill factor mainly affected in that case. Due to this barrier, there is a fill factor will be affected. Series resistance also will be increased because high defect density can trap the free carriers, and this basically reduces the mobility near the junction. So in extreme cases, a resistive interface layer, so called dead layer, sometimes at the interface is created, and which increases the series resistance, and if series resistance is increased, obviously the fill factor will be low. So this reduces the fill factor and hence the efficiency. Reduced blue response, again the photons with shorter wavelength is absorbed within a short length of the device in the front side, because which light will be absorbed, that depends on the wavelength or energy. So higher energy photons means lower wavelength photons will be absorbed fast in the front side. Lower wavelength, that is blue wavelength or UV, they are absorbed near the front surface. And if the front surface has a interface, so these interface defects, so due to presence of the different interfaces, so the generated carriers due to blue photons, blue color photons will be recombined. So blue response will be low. And if you measure the EQE, the external quantum efficiency, that can be also obtained from the SCAPS 1D simulator, you can see that in the blue region, this mainly affected. And hysteresis and instability, this is also an important, particularly in case of perovskite solar cell. Perovskite solar cell will also be demonstrated, simulation of that through SCAPS 1D. Anyway, in perovskite solar cell, perovskite is a material, a new material having a very good absorption coefficient and other favorable parameters for solar cell. It has been exploring widely. Anyway, for a perovskite solar cell, the interface traps can capture and release ions. So this capture and release, this process is a time-taking process, and so there will be a hysteresis in IV curves, and long-term instability under light and bias stress is observed. So these are the main effect of these interface defects. Now you cannot avoid, or you cannot totally avoid the interface defects. Only you can mitigate the defects, and several mitigation technologies or techniques are there. Say, important technique to reduce or to limit the interface recombination, it is called passivation. So passivation of interface defects, that can be done, say for example, by a chemical treatment. Chemical treatment means, suppose you used cadmium chloride treatment in cadmium telluride solar cell. At the surface of the cadmium telluride, if there are some cadmium chloride plasma or in gaseous form is flown, so some bonds or incomplete bonds are passivated, so they are making a complete thing, so interface states will be reduced. Alkali, suppose sodium, potassium, etc., these treatments in CIGS. So several techniques and mostly chemistries are involved here, so they may reduce the defects at the interfaces or at the surfaces. Interfacial layers, sometimes we use some interfacial or buffer layers, say namely titanium oxide, tin oxide or SAMs. These are the different materials used in perovskite solar cell for interfacial layers. And band alignment engineering is another technique In that case, you have to choose the buffer or emitter materials with a favorable conduction band offsets, not cliff type. It is called spike type rather than cliff type. That is thing. That is favorable means it should not obstruct the flow. We have to choose a buffer material in such a way that band diagram should be in favorable condition of the transport. And you know the band diagram at the interface depends on the material work function, electron affinity, etc. that can be controlled, that can be engineered so that the cliff type offset is converted to the spike type. In that case also you can reduce the effect of interface defects. And surface modification, so reduce the dangling bonds via some chemical treatment. So sulfide passivation, sometimes some amorphous silicon, this is through hydrogen, this is passivated through hydrogen, so that's why it is hydrogenated amorphous silicon is told. So basically you are trying to reduce the impurities either in terms of chemical treatment or in terms of band alignment engineering. So these are the possible mitigation strategies. Another strategies, these are all comes into the chemical type of passivation. But another passivation that is called field effect passivation are also important. Field effect passivation means you have to design the solar cell in such a way that the carriers should flow as per the desired direction. So with an example I will explain this. So this passivation sometimes may be a field effect passivation also. So in the case of field effect passivation, you see, so earlier whatever we have discussed, these are all chemical types. So these, if you see, these are all chemical passivations. Strategies, this chemical passivation. All these, whatever we have discussed, these are chemical passivation. But there may be some field effect passivation also. You remember that in a single crystal solar cell structure, there is a BSF layer, back surface field layer. That means we have a thick absorber layer, say P silicon, this is crystalline. On top of that, have a thin emitter layer, so N plus, this is say amorphous silicon or polycrystalline silicon. And in backside, there is a P plus region. This is called back surface field. P plus silicon. This may be obtained during the aluminum back contact preparation also. Whenever you are putting some aluminum back contact, there is a simple solar cell structure I am telling, not the park solar cell structure. In the park also, passivated emitter rear contact, you remember. So there is backside passivation is there. So passivation is very important. So this is say aluminum contact, and due to presence of this P plus silicon, what if you observe the band diagram, if I draw the band diagram, say P silicon, this is suppose the Fermi level aligned, and this is a P silicon, and here it is P plus silicon. So this junction between P and P plus. Here in P silicon, you see the minority carrier is electron, and this electron, suppose this is, I am putting this is electron, and this is hole. So these are so many electrons. Holes also are there, they are generated in pair, but minority holes are not important here because minority electrons are important, because this excess minority electrons, and these electrons should propagate from this direction to this direction for separation. So not here, due to presence of this P plus, one electron, suppose this is a carrier generated electron, when they come to flow in this direction, they will repel back due to presence of this electric field. So there is a offset for electron. So this is the called field effect passivation. That is, electrons are not allowed to go in this side. They are going in this side. So this back surface field, this is called also field effect passivation. Similarly, if you have an arrangement of such kind of layer here, suppose if you insert some, instead of P plus silicon, if you put some aluminum oxide layer, aluminum oxide has a fixed negative charges. So instead of this, if you have a fixed negative charges layer, then also the electrons will be repelled back. That is also called field effect passivation. Suppose you have now a new structure I am drawing. There you have in silicon, P silicon crystalline is absorber layer, and in back side, suppose you are putting some aluminum oxide. Due to presence of Al2O3, there is a interface charge in the fixed negative charges are there in the interface between aluminum and P silicon, and this basically repels the electron from here to here. So this is called field effect passivation. So due to presence of fixed negative charges, electrons movement is controlled. This type of passivation is also allowed, because if electron would come in this direction, they would be lost. They would be reaching in the back contact. This is not desired case. So this way field effect passivation is also possible. Anyway, so effect of interface defect will be demonstrated through simulation using SCAPS 1D by Said Anwar Askari.
So we know that when we are trying to fabricate any solar cell, so there always be a heterojunction interface, right? And there is a dominant mechanism that will affect the performance of the solar cell, that is the interface defect, right? So we cannot avoid interface defect, right? But we can minimize the interface defect. So how this interface defect will affect the performance parameter? So in this session we will analyze through the simulation by using SCAPS 1D. Okay, so for this simulation, again we will choose the same structure, that is CDT and CDS heterojunction solar cell, and we will apply the defect in between the absorber, that is CDS, and absorber, that is CDT, and the window layer, that is the CDS, right? So let us start the problem definition, we will click on the set problem. Now here you can find we have selected the same structure, that is the CDS CDT based heterojunction solar cell and SNOX as a TCO layer in this structure we have selected. Now how we can add the interface layer in between that is in between CDS and CDT, right? So let us load the already predefined structure. So in this structure we have added one CDT CDS layer. So let us click and on the CDT CDS interface layer, and how we can define. So first you have to define the name. So this is CDT CDS interface layer, right? And then we have to define its defects. So by clicking on that you will find one window will open, and here the different material defect property we have to define, right? So in this simulation we have considered the natural defects and the capture cross section for the electrons, that is 10 to the power 15 per centimeter square, and the centimeter square, the capture cross section for the holes is 10 to the power minus 15 centimeter square, and the Gaussian energy distribution I have selected. So for selecting the Gaussian distribution, here multiple options are there. Within that, more realistic distribution, that is a Gaussian distribution I have selected. And we know that the energy level where the defect is more effectively affect the solar cell, that is the mid gap, right? So that's why here we have selected the above middle of the interface gap and the zero value from the reference level we have selected. It means your defect energy level, that is ET, lies exactly in the middle of the interface gap, right? And that is the most effective position for the energy level for the defects, right? Now then we can see the Gaussian distribution characteristic energy and its density that we have selected here, that is 10 to the power 10 per centimeter square, right? So these are the parameters that we have selected for the interface defect, and by selecting the accept, we now tell me here we have it will display the parameter that we have selected, that NT, that is the concentration to the power 10 per centimeter square, and its peak value is 5.64 into 10 to the power 10 per centimeter square, and energy distribution, that is ET, that is above the middle of the interface gap, and that is 0 volt, that is exactly in the middle we have considered. Right. Now by using these parameters they have selected the surface recombination velocity at the interface. So we know that the surface recombination velocity is equal to what? That is the interface defect density NT into the thermal voltage VTH, right? It is a maximum threshold velocity VTH and the capture cross section. So from where we are getting the VTH? That VTH that we have selected from the material parameter. So these value in combine will give you the surface recombination velocity, that is Sn for the electrons and as well as Sp for the holes, right? And I will show you from where they have taken the VTH, that is the maximum velocity, threshold velocity, right? So in the material itself we have selected the electron thermal velocity here 10 to the power 7, here whole thermal velocity is 10 to the power 7 per centimeter per second. So by using this one they have selected the interface recombination velocity for the electrons as well as holes. Now we will analyze how this interface will affect the performance, right? So by clicking OK, we can accept all the material parameter for the interface, all the defect parameter for the interface, as well as these material parameter will be considered as in the lecture 50 that we have discussed. So by clicking OK, we can accept. After completion of setting problems, that is we have inserted the additional interface layer in between the CDT and CDS. Now we will go for the variation of the defect density in between CDT and CDS for finding the effect of the interface defects. So for that we can again go for the batch setup. So by clicking on the batch setup we will see one window. So within a window you can select the parameter which we have to vary for this simulation. So by clicking add you will find the list of the parameters. First we have to choose within which we have to vary the parameter, like here we will select the CDT CDS interface, right. So CDT CDS interface we will select, and within that which parameter we have to vary. So for that there are many parameters are there: relative mass, mass of the electron, interband, right, and the interface defect, right. So here we will select the interface defect, right. So this interface defect. So by selecting the interface defect, then we have to set the range of the value for which we need to see the effect. So there are two ways to define that one. Either we can define from and to and how many number of steps and its variation, that is log variation or linear variation, and it is better way to define in terms of the list, right. So by clicking on the set we can find the window where we can set the list of the interface defect parameter. So we will start from 1E10, then 5E10, right, then 1E11, then 5E11, then 1E12, then 5E12, then 1E13, then 5E13, then 1E14 and 5E14. So here we have varied the interface defect density from 10 to the power 10 to 5 into 10 to the power 14 per centimeter square, and then we will update the checked value list, and you will see there is a value is updated, and then update and OK. Now these value will be saved for the variation. By clicking OK we will confirm all the values. Now again we have to set the increment within a voltage. So how much voltage increment will be there? So this window will not sufficient to set the increment value for the voltage. So for that we have to go to the set problems, and from the numerical setting we have to change the variation. So here maximum voltage for the recording will be how much? So we know that in this structure the variation of the voltage will be affected by the open circuit voltage. So here open circuit voltage is 900 millivolt or maximum 950 millivolt. So he will choose the 1 volt, that is 1000 millivolt. And what is the stepping will be there? So for the stepping we will select 1 millivolt. So how we can select 1 millivolt there? So here by setting the minimum voltage increment for the recording of the solar cell characteristic, here we have selected 1 millivolt. So this is very important step for reducing the problem, that is a convergence problem, right. So by clicking OK we have already set this value from the numerical setting, and then by clicking OK we can accept, and then we can go for the recorder setup. So what are the parameter we want to record there? So first we want a cell characteristic. So we can choose from there. This is IV characteristic. So all the IV characteristic I have selected, that is efficiency, JSC, VOC, fill factor, maximum power point for the current and the voltage, right. So and other, that is the defect parameter that we have selected, and this is the recombination parameter that is majorly affected by the defects, right. So other parameter we can also select, like its band parameter. So from the energy band parameter we can select its electric field. So is there any variation of the interface electric field with respect to the interface defect? So let us see that one. So by selecting the electric field, so here we can select by selecting that one in the below. So all the parameter that we want to record, that we have selected there, and OK, and then we have to run for the batch recorder. It means all the parameter we can record there by clicking the calculate record, right. So here by calculate recorder will give you the effect of the interface defect on the all the parameter that we have selected in the recorder, right? And it will extract from the either IV characteristic or the generation recombination characteristic, right? So by clicking on that, we will start the. So before that, we need to choose. So what are the different optical property will be there? That is which in which spectrum we want to simulate. Like here we have selected the AM 1.5 as a simulation spectrum, right? And we have selected the 300 Kelvin as a by default temperature. And what is the working point? That is by default that we have selected there. And then we will see the effects of the interface defect on the performance parameter of solar cell. And this effect will be dominant where the dominant effect defect, that is the interface defect in between the absorber and the window layer. Okay. So now the simulation is started. We have to wait for the completion of the simulation. After the completion of simulation, now we will analyze the result. So we have set it the variation of the interface defect density from 10 to the power 10 per centimeter square to 10 to the power 5 into 10 to the power 14 per centimeter square. So now the simulation is completed. We will see the result. So by clicking on the results of the calculation, we will see the result. And here we will see the recorder. Okay, so whatever the parameter that we try to record, we can see there. So before that, let us see how there will be a change in the IV characteristic. So by clicking on that IV characteristic, we can easily see what are the different IV characteristic. This is due to the different defect density, right? So here the batch 1, so in the batch 1 we have selected the 10 variants, right? So let us see one by one. So when the doping interface defect density is very low, that is in the order of 10 to the power 10 per centimeter square, so we can see that the VOC is maximum. So in the each step we will see there is a variation in the VOC, and you can easily realize in this area. Now I am varying, you can just easily focus on this area. So by changing the steps, so you can see that there is a variation in the VOC. But all the parameters in summary we can realize through the main window, that is the result of the calculations. By clicking on that, you will find one tab, that is the recorder. Okay, so you can click on the recorder tab. So by clicking on the recorder tab, you will see one window. Say this is the results of the batch recording, right? This is a panel related to the results of the batch recording. So in this panel, you can easily see that the efficiency is reducing by increasing the total density, that is interface defect density. So to get more clarity, you can set this in the log scale. So x axis in the log scale and y axis in the linear scale, right? So now you can easily see there is a variation in the efficiency by increasing the interface defect density between the absorber and the window layer, right? So at the low defect density, interface defect density, your efficiency is 16%, but at the higher defect density, the efficiency of this structure will fall down from 16% to 11.7%. Now, what is the reason behind that? So that is the important parameter. So how we can analyze the reason behind that, there is a, what is the reason of reduction of the efficiency. So that we can analyze by seeing the another property, that first we will see the other characteristic, cell characteristic, right? So the VOC, now you can see that there is a variation in the VOC from 870 millivolt to 840 millivolt. Now the JSC is also reduced from 24 milliampere per centimeter square to 20.5 milliampere per centimeter square. Major variation you can find in the fill factor. So it is 76% to 68%, right? And then we will see there is a variation in the maximum power point in the current and the voltage. So these are the effective parameter that we have characterized from the IV characteristic. But what is the reason behind that? So we will see the recombination. Okay, so which type of recombination is dominant one? So we will see there is a large variation in the interface recombination. Now if we will set the log scale of the y-axis, you will see at the lower defect density, that is 10 to the power 10, your interface defect recombination is very low, in the order of -1 to -2. But by increasing the interface defect density, the interface recombination have increased and reached till 100 milliampere per centimeter, right. So this value is 10 milliampere, right, across that. So this value is, there is a 2 order of increment approx from low defect density to the high defect density. So this is the major reason behind that reduction of the efficiency. Okay. So in that way we can analyze the many parameters here: left contact, the variation in the left contact, and the variation in the right contact recombination, right. So you can find that there is a major variation across the left contact recombination, right. These are the energy band. So this is the conduction band and valence band energy levels, you can easily analyze from this. Okay. So the lower value is not visible there, so for that we can set the manual scale. So lower value is below that one. So let us see by putting -3 here, even at the -3. So this is the electric field. So we can see that there is a large variation in the electric field also. So -3 to -9 we can set. Okay. So close to that, the electric field is, there is a sharp variation in the electric field or reduction in the electric field, right. So in that way we have analyzed what is the effect of the interface defect density. So how we can minimize this effect? So by reducing the interface defect density through any spacer layer or through any additional layer. Okay. So now we have completed to see the effect of interface defect on the performance of the solar cell.
Perhaps you have gone through the simulation, how you can observe the effect of interface defects by changing the defect density, how the performance of the solar cell is varying. You observed through simulation. Thank you.